In this lecture, we're going to review an idea from mechanics, that of work and energy, because we're going to be using it throughout the rest of the semester in our study of electric and magnetic fields. So basically everything here comes from the previous semester's course, and then we'll see in the next lectures that it translates over very directly to the ideas about electric potential energy, and then a new concept called the electric potential. So today we'll talk about just an overview of work and energy, potential and kinetic energy. We'll talk about how to calculate the work, which is the thing from which all energy concepts are derived. And we'll talk about three different ways of that calculation. And of course, there's a single definition of the work, but it's a pretty complicated mathematical definition, and in general, we'll use some simpler forms of it. Then we'll derive a potential energy function. So there are specific kinds of forces called conservative forces, and for each of those forces, there's something called the potential energy, and we'll show how to get that. We'll talk about the work-kinetic energy theorem, which together with the idea of potential energy leads to this concept of energy conservation. And finally, we'll just quickly review how you go backwards. So we derived a potential energy function using a conservative force, but once you have a potential energy function, that implies the conservative force field as well. So we'll talk about that at the end. And in the next two lectures, as I said, we'll apply it to the topics of this class. So next time we'll talk about electric potential energy, which is just a new electric potential derived from the electric force. And then we'll introduce this slightly differently named thing, the electric potential, which is given by V. For just an overview, I think there's a couple things to mention right up front. So one is that energy is the topic that we're going to discuss today, and it's not independent at all from Newton's laws. In fact, it's derived exactly from Newton's laws. So the topic of energy just provides an alternative way of looking at mechanics and an alternative way of calculating things in mechanics. And as you saw in 230 or 220, it sometimes is easier to make a calculation using energy than it is using, for example, Newton's second law. So that's part of the reason that we use it. Another reason that we use it is that much of theoretical physics in general has sort of been translated over into the concept of energy. For example, high energy physics, the physics of the Standard Model, all of these things from modern physics are now often thought of just in terms of energy. And so we think of this as sort of a more basic way of looking at the universe. But again, not independent from Newton's laws, it's just an extension. It's not even an extension, it's simply the same material written in different language. The second thing that we should mention up front is that everything about energy comes from this single concept of work. So if you have a force, then you can define the work done by that force over a path. And so you need to understand what that is in order to understand everything else related to energy, because all of it comes directly from that. So let's start there. So the definition of work is the work done by a constant force F over a straight line path, delta R. And I'm going to underline that entire thing because the definition corresponds to every piece of that statement. So let's try and show what that means. So if you're dragging a box across a floor, let's say that you have some tension force that's being applied to the box. As you move that box, it's going to go from one place to another, and so maybe it will end up over here in the end, and you'll end up over here as well. So we call that the displacement of the box, and we should draw that as a vector. And in this particular example, it is a straight line displacement that we're going to use. And so let's draw that straight line displacement. You go from this point to this point, and that is your delta R vector. So the work done by a constant force, we'll assume that this tension force is constant in time and it's constant independent of where you're standing, over a straight line path, which can be represented by this displacement vector, is defined to be work done by the force is equal to the force vector dotted together with the displacement vector. And this is just the scalar product, which you know means magnitude of the first vector times magnitude of the second vector times the cosine of the angle between the two vectors. So if you want to figure out what that is, then you take those two vectors and you put their tails together. Well, that's not really the force, is it? Here's the force, here's the displacement, and this angle is the angle between the force and the displacement. So in this case, you would get slightly less work done because the force is angled. If you were to sort of squat down and pull directly in the same direction as the displacement vector, then this angle between the force and the vector would go to 0, and you get the maximum amount of force, the maximum amount of work for that particular force. So that's the work done by a constant force over a straight line path. Now, in general, we'll talk about the work done by forces that are not constant, so they might be changing over the path, or paths that are not straight. So this is one example of a path that's not straight, and usually we talk about a path as like a curve in space. So sometimes we write that path with like a C here. And if you want to calculate the work over that entire path C, so maybe I should call this the work, well, it's the work done by the force over the path C, then it's going to be the sum of the works over little straight segments. So we already have a definition for the work done over a straight segment, a small short straight segment where the force is constant. So we can simply add up the works done over each of those segments. So we could draw little vectors here. Here's the tension force again, and here's the short little delta R vector. Maybe in another position we have the tension force here, and we have the delta R vector here. So you can imagine that you can simply use our initial definition, take the dot product of those two vectors, and then add up those little works, the WNs, over each little segment. And of course, what that's going to end up with is a Riemann sum, which can become an integral. So in general, finding the work means to calculate an integral of the force dotted together with the displacement vectors. So let's look at what that means here. So this thing would be from n goes from 1 to capital N of the force at a particular chunk n dotted together with the displacement at that particular chunk n. And you should be able to sort of, if this is an approximate expression for the work, then that will eventually become an exact expression for the work, where you have the integral over that path of the force dotted together with the infinitesimal displacement. And I'm just going to put quotation marks around this because just like with every integral, it's just symbolic notation, and there's actually a more precise way of writing this quantity here, but you can see it sort of comes nicely out of that there. That's the most general expression for the work, but we're hardly ever going to use this general expression. Instead, we're going to use things that are a little bit easier to calculate, either the work done by a constant force over a straight path, or in some applications we can find sort of an intermediate expression, which is the work done by a changing force. So maybe the force changes over the path. So one example of this that we'll do in a few moments is the work done by a spring force, which you know depends on the position of the object. So if you have some coordinate system, x, where that coordinate system is set up so that x equals 0 is at the natural length of the spring, then the force opposes displacements from that equilibrium position. So the force points like that. And you can see that as I were to, if I were to take this box and move it from the equilibrium position outward, then that force will be getting larger and larger and larger because, well, I'll just write it down, the x component of the spring force is minus kx. So its magnitude gets larger as the x value gets larger. So in that displacement, you can think of it as a straight line displacement, delta r, but the force is changing at every point along delta r. So you really need to divide it up into little short delta x segments over which the force is constant, and that thing will lead to a Riemann sum in x, which then leads to this expression here, which is a less complicated looking integral than this one here. This one, it's not quite clear what that means, an infinitesimal vector segment. But this one is pretty clear. So this is just a regular integral over x from the initial position to the final position of the x component of the force, which of course could be a function of x. So if you want to calculate the work done by a changing force over a straight path, then you call that path the x-axis, and then you set up this integral over that straight path. And we'll do that in a couple of different examples. So as I mentioned before, everything energy related will come from the work. So we'll talk about conservative forces. A conservative force is the work done is path independent. So notice in our definition of work, we said the work done over a particular path. If you were to take a different path, so instead of going straight across the ground, maybe I went up and down, it's possible that the work done would be different. Well, if it's not true, if the work done doesn't depend on which path you take, then you call that a conservative force, and we'll show an example of that. If we have a conservative force, then there's something that you can associate to it called the potential energy, and so we write delta U of the conservative force is defined to be minus the work done by the conservative force over some path between 2 points. And then the kinetic energy is also defined through the work through something called the Work-Kinetic energy theorem, which says that the net work, which you could also write as the work done by the net force, and that is equal to, basically by the definition of kinetic energy, to the difference in 1/2 mv squared. That's how we define kinetic energy. And then finally, we have energy conservation, which looks something like the initial kinetic plus the initial potential is equal to the final kinetic plus the final potential, which is true if you only have conservative forces acting. If you have non-conservative, then you have to adjust that slightly. So everything comes out of that. Let's do a few example calculations with work. So we'll do 3 of them, and we'll use the 3 different particular calculations of work that were mentioned above. The first being if you have a constant force straight path, then if you have a straight path but a changing force, and then finally an arbitrary path. So for a constant force straight path, constant means constant over the path that you choose. So the simplest example of this is the gravitational force near the surface of the Earth. So if I have like a table here, and I take a book here, and I want to move that book from one point in space to another, let's say that I want to put it up on top of the table, so it's going to end up here. Then I could take a straight line path from the initial to the final point and call that the delta r vector. So that's a straight line path. And at any point in that path, you have exactly the same force, gravitational force, acting on the book. So here's the book at one moment, and there's a force, which we call the force of gravity. But of course, the force of gravity has magnitude mg. So you notice that that expression for the force, it doesn't depend on where it sits along here. It doesn't depend on the height, doesn't depend on the x position. So that is an example of a force which remains constant along the path. You could just drag this vector everywhere along that path, and the force is constant. So let's calculate the amount of work that the force of gravity does as you raise up that book. So we write down the expression. So as you see, there's sort of a qualitative idea that has to happen up front, which is deciding which of the work equations you're allowed to use. And so because I have a constant force over a straight line path, I can use this expression for the work, which is the work done by the force of gravity is equal to the force of gravity vector dotted with the displacement vector, like that. Okay, now let's put some constants in here. Let's say that the table is of height h, and it's going to go over by a distance d, maybe. And let's try and figure this out. So the work done by the force of gravity is this, and that thing means that we have the magnitude of the force of gravity multiplied by the magnitude of delta r times the cosine of the angle between the force of gravity and the delta r vector. There's a couple ways that we can do this. So one way is we can look at that angle. So let's see. If we have the delta r vector that looks like this, and we have the fg vector that looks like this, then this is going to be the cosine here. And you can see that because these things point in opposite directions, you're actually going to get a negative value for that expression. And the cosine of that angle is actually going to be this length over this length here. So it's going to be negative times this, the cosine of this angle. So let's take a look at that. So what is it going to be? It's going to be mg, and then we could just call that the magnitude delta r, like that. And then there's going to be a negative, and if you look at this triangle here, there's an h and there's a delta r here, so it's going to be minus the cosine of the angle, which is going to be h over delta r. So the angle here is this, and the cosine of that angle is going to be negative h over delta r. So what do we get? We get that the work done by the force of gravity is equal to minus mgh. It's a negative work because you can see that at every point along the path, the force points sort of opposite to the displacement vector. And so that this dot product will lead to a negative work. If you were to ask a different question, what's the work done by the normal force holding that book up as you raise it to the table? Well, then the displacement would point in sort of the same direction as the normal force, and you get a positive work. So you see that it's important to recognize that work depends on the force that you choose. So the work done by the force of gravity is negative here. Gravity is also a conservative force, and so what we could do is we could look at it over a different path, and we should find that the work done is the same. So maybe we should quickly do that. So if I were to take the book and just raise it up here and call this delta r2, so now my book goes like that. What I should find is that the work done is the same. So if I do the work done by the force of gravity over the second path, then that's going to be equal to the force of gravity dotted with the delta r2 vector, which is going to be the magnitude of the force of gravity times the magnitude of the delta r2 vector times the cosine of the angle between the force of gravity and the delta r2 vector. And what is that? Well, it's mg for the magnitude of the force of gravity. The magnitude of delta r2 is just h, and then the cosine of the angle, well, if we were to draw those two vectors now, we have delta r2 and we have the force of gravity the angle between them is 180, so we get a -1 out of the cosine of the angle. And you see we get exactly the same result. So that's certainly not a proof that gravity is a conservative force, but if our definition of conservative force is that the work does not depend on the path taken, then you could take the book up at an angle. You could also take it straight up. I guess I should have said at an angle or going across, and in this place the work done would be 0 because it's perpendicular to displacement, plus the work done going straight up. Those two have exactly the same result. So the gravity is a conservative force if we were able to, we could prove that if we were able to show it for all possible paths. We're not going to do that right now. So changing force, straight path. As I mentioned before, the spring force is a nice example of this. So let's just take an example of that. So remember, we choose a special coordinate system when dealing with a spring force. We place the origin at what's called the equilibrium point, and that means that if the object were sitting at the equilibrium point, there would be no force on it because the length of the spring is its natural length there. If it's pulled to the positive x direction, then there's going to be a force that points in the negative x direction, and that will look like this. That's the force of the spring. So let's say what is the work done by the force of the spring from 0 to positive d. So that will be a force which is changing over the path, but it is a straight line path, and so I can choose my delta r, not my delta r, but my path to be the straight line of the x-axis. And if I do that, we can use the equation that I wrote down before, which is the integral from the initial x position to the final x position of the x component of the force, so I guess I should call that the x component of the spring force, as a function of x integrated over the x-axis. That's the definition of the work over a straight line path. And you can get that by doing a Riemann sum of our simple expression. You can take a look at older lecture notes from 230 to see that that's true. So what is that thing? Well, let's plug in for what we have. We're interested in going from initial x of 0, final x of d, so let's plug that in. Our spring force, well, remember what our spring force looks like. The magnitude of the spring force is equal to k times the absolute value of x, and the x component of the spring force, we want to express that for positive x values, it points in the negative x direction, so we write that as minus kx. That's the x component of the spring force. And in fact, we could say, well, that's a function of x, so that's the x component of the spring force as a function of x. So let's plug that in. So we have minus kx and dx. So what do we find? Well, we find that we have a minus k out front, then we have the integral of x, which is x squared over 2, evaluated from 0 to d. So we get minus k times d squared over 2 minus 0, or minus k d squared over 2. Let's just look at that qualitatively for a second. We found a negative work in the work done by the spring force as you move it outwards, and that makes sense because over every single little segment, delta r, you see that the force of the spring is in the opposite direction of the displacement as we're moving along there. So that will give negative values of the work, and then you add them all up and you'll get some negative value. Okay, now finally we have an arbitrary path. And I'm just going to write down what the work is, what the equation for work is in the most general sense. The work done by a force over an arbitrary path C is equal to, and I wrote this down in the first page as the force dotted with this infinitesimal displacement vector. But this thing means it is the force dotted with the velocity vector at every point integrated over time. So actually, this integral just becomes a regular integral over time where you have some initial time and final time. So what that means is if I were to take like the skier problem that you see in 230, where you have a skier up here at the top of the hill and you're going to do a conservation of energy problem. Well, one thing that you might not remember is that there's a non-conservative force acting in that system, and that non-conservative force is called the normal force. So the normal force is changing all the time, so we don't call it a conservative force because the work done by the normal force is zero everywhere. So you could say that the work done doesn't depend on the path, but we don't generally call the normal force a conservative force. The normal force there is pointing in that direction, and over any little segment, the delta r is pointing perpendicular to the normal force. And the other thing that points perpendicular to the normal force is the velocity of the object along the path, the velocity of the person as they go down the hill. So the way that you do this in general, and we're not really going to do it in an exact calculation, is you determine a path here, and what you do is you say, well, that path can be represented by a position vector over time. So I could say, well, at this moment in time, there's a position vector that comes from some coordinate system, that's r of t, and then the derivative of that position vector is what we call v of t, and that thing is what goes inside of the work integral here. So that's the precise statement of how to calculate the work for a generic force on a generic path. But as I said, we're not really going to do that at all. However, this idea of the normal force being perpendicular to the velocity, well, you can see that f dot v is equal to 0. So at every point on this path, the work done by the normal force is 0, and the work done by the normal force total is equal to 0. So we might use that concept that if the force is perpendicular to the velocity vector, meaning the derivative along the path, the tangent vector to the path, then the work done will be equal to 0. So we might use it in that case. Let's derive the potential energy. So first we should talk about what we mean by potential energy. We talk about a force being conservative if the work done between 2 points in space does not depend on the path taken. And if you have a conservative force, then you can define this thing called the potential energy. So if we say that there's a conservative force Fc, and I call it a conservative force field because the idea is that for any point in space, r, you should be able to tell me what the force is, then we define the potential energy due to Fc, and we should say between 2 points in space, so like from point A to point B. And so let's just, we'll do this example a little bit later on the page. If we have like a big mass m and a little mass m, and we take some path from some point A to some point B, so that's like A and B, then you could represent those as positions relative to some origin. For instance, an origin which is at the center of the big mass. So we're going along this path C from A to B, and we want to calculate the potential energy from A to B due to that force. Well, the definition of a conservative force is that the work done doesn't depend on the path, so you really can take C out of the equation completely because it doesn't depend on which C you choose. I could have chosen this C if I wanted to, or this C, or this C. So the result turns out to be just the work done by the force from initial to final. It depends on the endpoints, where you start and where you finish, but I didn't write a path here because it doesn't matter which path I take. In fact, I can calculate it. And I screwed up the equation. It's minus the work done. That's important. So in order to find potential energy, the change in potential energy, you have to calculate the work between 2 points, and then the opposite of that value is what you call the change in potential energy. So we'll do that in a couple of examples here. So let's do the potential energy of a mass in a uniform gravitational field. We said, well, if you have this book and you raise it up here along some delta r, then the force of gravity, which we said is a conservative force, will yield a work done. So the work done by the force of gravity was equal to minus mgh here. What we can do is we can give ourselves a coordinate system, and we can make that a little bit more general. So if we have a coordinate system that's called y, where y is pointing in the vertical direction, then we can say that the work done by the force of gravity from y initial to y final is equal to minus mg delta y. Now we can apply our definition of the potential energy up here. And so the potential energy due to the force of gravity in a uniform gravitational field, delta U, we'll call it little g, is equal to minus the work done by Fg, which is equal to plus mg delta y. So that is the difference in potential energy between one point and another. So the difference from the book going from the ground to the table is a positive gain in potential energy of mgh. We should mention one last step, which is that we usually talk about a potential energy function, which is a function of a single variable, not of a difference in positions. And the way that you do that is you define a 0 point in the potential energy. So we define, meaning we choose, that ug at y is equal to 0 is equal to 0. And once we do that, then what do we get? Well, this equation tells us ug of y final minus ug of y is equal to 0, and let's just call this of some value y. So if I choose, so let y final equal y and y initial equals 0, then the right-hand side of the equation is mg times y final, which is y, minus y initial, which is 0, and we get u g as a function of y is equal to mgy. So that's a slightly different expression, and that's called the potential energy function. So let's just review the steps quickly. We want to find the potential energy in a uniform gravitational field. Because the work done because the force is constant and the path is straight, we can calculate the work done using our simplest expression for the work. And we did that before. We found it to be minus mgh, which you could also write in this coordinate system as minus mg delta y. Then we use the definition of the potential energy, more precisely the definition of the difference in potential energy between 2 points, to get plus mg delta y. And then we define a 0 point of the potential energy. So we have to state this explicitly, that I chose the floor to have 0 potential energy. Obviously, if I can do that wherever I want, then it doesn't really have much meaning, but that's the way that we define a potential energy function of a single variable. And so we plug that in, we make the choice of arbitrary y final, 0 y initial, and then we use our statement that u of 0 is equal to 0 right here, and therefore we get ug of y is equal to mgy. And that's the process we'll use every time to find a potential energy function. So let's do a more complicated example. And this is a useful one because it translates over almost exactly to the case of two charges. So what we're going to talk about is the gravitational potential energy between two masses. So I'll talk about a big M and a little m. And maybe I'll give myself a little bit more room here. And what we're going to do is we're going to take this little m and we're going to move it from one point in space to another point in space. And we're going to calculate the difference in the potential energy between those 2 points in space. So we could choose a path to move that looks like this. So that's one possible path. But it's going to turn out that we don't want to do that. And the reason is we want to be able to make our calculation of the work and then the potential energy from that in the simplest way possible. And because gravitational potential, or because the gravitational force is a conservative force, then we know that we can take any path that we want. So instead of taking that path, we can take a path which is more useful, meaning one which is straight out to there. Let's make it a little bit longer. And then one which is curved here. So that will be my path. And we could call that C2 and C1, those two pieces of the path. And you'll see why I choose that in just a second. So we're calculating the gravitational potential energy, so that means we're trying to find U of big G from point A to point B. And those are, if we just draw a little side picture, we're going from this point to this point. If I chose an origin at the big mass, I'm going from this position to this position here. Okay. So let's write down the definition, and that is that it's minus the work done by the force of gravity from point A to point B. Okay. Now, in calculating a work, I need to know what sort of equation I can use. And the reason I constructed my paths like this is because I have a straight line path right here. And so what I can say is I have the work done by the force of gravity from along path C1 plus the work done by the force of gravity along path C2. And in this case, we have straight line. And then let's quickly take the second case. In the second case, we have, well, there's a force of gravity that points, it's an attractive force of gravity, so it points directly inward towards the big mass. And then our velocity vector points along the path, so those two things are perpendicular. So in the second part of it, we have the, we use the arbitrary path expression, which is along C2, the f dot v dt, but that whole thing is equal to 0 because of the way that I constructed the path. So that curved path is a circle around big M, and the force points exactly perpendicular to that circle, so therefore that part is equal to 0. So what I'm left with is just the work done along the first path, and I've lost a minus sign in all of this. So we have minus that thing here. So here's my minus sign. And then on the first path, C1, I I chose it to be a straight path, and the force is changing along that path. So I can use that other definition of the work. So here's my force at some position here, force of gravity, F big G. And so I can choose that straight line to be an x-axis. So I'm going to do that. So here's my x-axis. And along that x-axis, let's put my origin of the x-axis at the mass there. Along the x-axis, I have an x-initial, which we could call RA. And we have an x-final, which we could call RB, because of the way that I've set up the path. So the distance from the center of the big M. Okay, now we can write down the expression. So it's the integral from x initial to x final of fg, the x component, as a function of x dx. Now we can calculate that. So from x initial is called RA to x final is called RB. And then I can plug in the expression for the force of gravity. Remember, Fg is equal to big M, little m, big G, big M, little m, over r squared, where r is the separation of the two masses. That x value, the x component means that the force should be pointing in the opposite direction as the x value. So we have a minus sign out front, just like we did for the spring force. So we get minus big G, big M, little m, over, and then this r value in the definition of the force, well, by putting my origin of my x-axis here, the r value is exactly the same as the x position. So I can just replace r with x here. So I have x squared dx. So this is the x component of the force of gravity as a function of my x value. Okay, and now I can just calculate. So I have two minus signs, those cancel out. So I get, I get big G, big M, little m. The integral, what's the antiderivative of x to the minus 2? Well, it's minus x to the minus 1. And I go from RA to RB. So what does that become? Well, it becomes minus GMM over RB minus GMM over RA. Is that right? Looks like it's right. Okay, and now I need to, I guess I should add myself another page. Because I want to find the potential energy function. So I found that delta U of big G is equal to, from RA to RB, is equal to minus GMM over RB plus GMM over RA. And I want to find a function, UG of R. And the standard assumption that's made about the zero value for the potential energy is that the potential energy between two masses goes to zero when their separation goes to infinity. So we're going to assume, or choose, that UG of infinity is equal to 0. So we're going to look for a UG of R, but when R goes to infinity, it's going to be equal to 0. So let's then make the choice that the initial value is equal to infinity, and the final value is equal to some value r. So what do we get then? Well, we have UG of final, RB, minus UG of initial is equal to minus GMM over R final, R. So I guess I should have called this final, oops, R, and this is infinity, initial, plus GMM over initial, which is infinity. So what happens? Well, anything over infinity goes to 0. We assumed that the potential energy when they're infinitely separated is equal to 0, and so we get that UG of R is equal to minus GMM over little r. Now we'll consider energy conservation. And energy conservation rests on two things. One is what we just talked about, which is that there are certain forces called conservative, and you can associate a potential energy function to those forces. And the other is this thing called the work-kinetic energy theorem, which basically defines this quantity called kinetic energy, which you know to be 1/2 mv squared. So the first thing I want to do is show you how we derive the expression for kinetic energy. It's not really a derivation of the work-kinetic energy theorem, it's more like a definition of kinetic energy. And it comes directly out of Newton's second law. So from Newton's second law, we know that we're interested in the net force on objects. And we can talk about something called the net work as being simply the sum of the works due to each of those forces. So like in this particular example, the work done by the gravitational force plus the work done by the normal plus the work done by the force of friction over some path. So maybe it's going to move from here to here over delta r. But of course, because you can add up those forces as vectors, and their addition is defined to be the net force, you could also call that the work done by the net force. So the net work is the sum of the works. It's also the work done by the net force. And the work-kinetic energy theorem is a statement about the net work. So let's see what that is. So the net work, in general, is equal to the sum. So if we separate it into little chunks of the network over some little segments, and that's going to be equal to the net force dotted together, the net force at a particular segment I dotted together with delta r at that I. So what we're talking about is maybe these forces are changing and I have to separate it into little segments, little delta ri. And I break that up maybe into capital N segments like that. The total is the sum of all those things. Now what is the net work, the net force? Well, the net force by Newton's second law I can write as the mass times the acceleration at that little segment I. So that's going to be dotted into the delta r I. Now I could do this completely generally. The work-kinetic energy theorem is completely general, but it's easiest to show it just for the one-dimensional case. So I'm going to assume 1D motion, meaning, for example, in this picture up here, I could draw an x-axis that points along the ramp, and that would be my one-dimensional motion. So if I have one-dimensional motion, then I don't have to worry so much about the vectors, and I can write this thing as the ax times delta x here, right? That's just the first term in a dot delta r. And the ax I can write as delta vx delta t, And delta x over delta t I can write as Vx. So this becomes m delta Vx, Vx. But that thing is actually a sum. So notice I took delta x over delta t, it became delta Vx. It became Vx by definition of Vx, but this thing itself is a Riemann sum over delta V. So if this thing is approximately the total work done over some segmented path, then it's going to be exactly equal to m, the integral, from some initial v to some final v of v sub x dvx. And what is that? Well, it's going to be Vx over 2 from initial to final, and that thing is 1/2 m v final squared minus 1/2 m v initial squared. That thing is what we call kinetic final minus kinetic initial, or delta k. So we find that the net work, the work done by the net force in some system over some path, is equal to the change in what's called the kinetic energy. But of course this is really just the definition of kinetic energy. That's where kinetic energy comes from. It comes out of Newton's second law as applied to a work. So that's the work-kinetic energy theorem. And now we can talk about energy conservation. So the basic statement of energy conservation is that if you have some system with a net force, then you could separate the net force into a set of conservative forces and a set of non-conservative forces. Because a force is either conservative or not conservative. So you go to each of your forces, you decide if it's conservative, and you call it a conservative force. So what does that mean? It means that the net work, which is equal to the change in the kinetic energy of the system, can be expressed as the work done by the conservative forces plus the work done by the non-conservative forces. And I'm just going to group them all into a single one. So we used work-kinetic energy theorem. Then we just used the definition of the net work, which is that it's the sum of the works. And now we can use the definition of potential energy. So remember, the potential energy difference for a conservative force is minus the work done. So these things become delta U of the conservatives, and then this is just the non-conservative. So what does that lead to? Well, this thing is kinetic final minus kinetic initial. And this thing is, let's just group all the conservative forces into one. So this is minus U final minus U initial. And then we have work non-conservative. And if we just group initials together, then we get kinetic initial plus potential initial is equal to kinetic final plus potential final, and then we have a minus the work done by the non-conservative forces. So this is a statement of energy conservation, which, as you see, comes from conservative forces and the work-kinetic energy theorem. Now let's do an example with conservation of energy. So this is called the escape velocity problem. And the question is, if you put a rocket, maybe somewhere here in Germany, what sort of initial speed does it have to have such that it can escape Earth's gravity, such that it can go off to wherever it wants to go in the universe? And the way that you answer this problem is you just do a conservation of energy problem. So there's some radius of the Earth, there's some mass of the rocket, there's some mass of the Earth, and you can just set up, since the only forces involved here are gravity, which is a conservative force, then you can say, well, if I have an initial energy, so let's call it mechanical energy initial, then that should be equal to mechanical energy final. And what are the energies that I have? Well, I have kinetic energy initial, and I have potential energy due to gravity initial. And then in the final case, I have some kinetic energy final and some potential energy due to gravity final. What we'll assume is that we'll let the final velocity of the rocket go to 0. So what that means is the rocket reaches infinity and stops. Now you could give it some velocity there so it could continue on its way, but you don't have to. So, okay, so now we have, so the idea is that you apply some force to get the rocket off the ground, but you consider it immediately after you apply that force. So, the thrust on the rocket is going to be some non-conservative force, but you can imagine just applying one big push immediately at the ground, and then it will have some initial velocity, and from that point on it's only governed by gravity. Okay, so what do we have here? Well, we have 1/2 mv initial squared for the kinetic energy initial. The expression for the potential energy due to gravity we found to be gmm over r, and that's r initial. And then the potential energy final is gmm over infinity, because I want it to go out forever. And so that becomes 0, because anything over infinity is equal to 0. And then we find that 1/2 mv0 squared is equal to gmm over r initial, or the initial velocity that you need to escape to infinity is going to be, the m's cancel, the 2 travels over, and we get 2 gm over r initial, but r initial was just the radius of the Earth. So we find this for the expression. So that's the initial speed that you need to escape the Earth. The final topic is to talk about going from potential energy functions back to forces. So we found that, let's just write it, sort of sketch it out. The potential energy due to a conservative force is minus the work done by that force, which is somehow the integral, minus the integral now because there's a minus sign, of the x component of that force integrated over x. So you see sort of the relationship between the potential energy and the force is that the integral of the force gives you the potential energy, very roughly. Well, it turns out that the opposite is also true, and the statement is that for a conservative force, F, let's call it F conservative, with potential energy function U, and the U depends on position, R, we can write that the force at any point in space, so maybe I should write the force at any point in space, is equal to minus the gradient of the potential. Now this uses some math which you might not see until Calc 3, so you might not have seen it yet. The gradient is defined in terms of this nabla vector, and so nabla means I hat partial x plus j hat partial y plus k hat partial z. So it's a vector of derivatives. And so this is a little bit complicated, and we won't really use it that much to do a complicated mathematical calculation, but it's nice to see that you can actually use it in, for example, one dimension. So let's look at one of our conservative forces, which was the force of the spring. So we found that the potential energy for the force of the spring, well, we found that the work done by the spring looked like 1/2 kx squared. The potential energy, it turns out, is 1/2 kx squared. And so what we should find is that the force of the spring in the x direction should be equal to the derivative of u with respect to x. And since there's only one variable, it's really just a regular derivative, not a partial. And then we have that minus sign. So this expression here, minus the gradient of u, in one dimension just corresponds to the first term, d dx. And so we get minus d dx of u for the force. And because we're talking about only one component, we're talking about the x value, the thing that multiplies I hat. So it's the x component of the force. So if that's the case, then what do we find? We find minus, and then we have 1/2 k 2x, which becomes minus kx, which of course is the expression for the x component of the spring force. What about for the force of gravity? So we had that ug as a function of r was equal to minus big G, big M, little m over r. Again, that's just a single variable. So what we can do is we can say that the force of gravity as a function of r and the r component of it is equal to minus du dr. So what is that? Well, it's minus, and then I take the derivative of this thing, I get back minus gmm over r squared. And so we find that the force of gravity is equal to plus gmm over r squared, the r component of it. So the derivative is, we gotta write in this thing here a little bit more carefully. So it's the derivative of minus gmm over r. Those minuses cancel, but we get back another minus from the derivative. So we get plus minus gmm over r squared. So the r component of the force of gravity is negative gmm over r squared, meaning that the force is attractive, which we know from the force